Okay, so wait, am I recording already? Oh yeah, it's perfect. Okay. So the first thing I want to do is I want to show you how this um, how this inner product actually works on an example. Okay. Okay. 2 times p of x times q of x dx. Okay, and our space is the polynomials of the third power. Okay. And of course, that's why we have the basis 1x, x squared, x cubed. Okay. So before we actually calculate, uh, yeah, before we actually, so yeah, so this is going to be the basis, our basis, the one that they're talking about, 1x, x squared, x cubed. This basis is perfectly adequate for expressing it. Okay, so before I actually go into the gram orthogonalization process and find an orthogonal basis, what I'm going to do is I'm going to show you how this inner product works on a particular um, on a particular pair of vectors, so it can make the calculations that I'm going to do make more sense, and also to give us more of a feel of what's happening. Um, you know, when you first think about the inner product, the scalar product, you know, originally when we look at it, we look at it in terms of like maybe you're in calculus 3, maybe you're in physics 1, you're learning vectors, you learn some nice things about the dot product, such as, for example, the fact that the dot product is 1 um, uh, if the two vectors are unit vectors that share the same direction, -1 if they're unit vectors and they are anti-parallel, that is to say they're on the same line but in opposite directions. We learned that if you take, we learned that we can find the angle between two vectors, like let's say like this. Let's say this is u. Let's say this is v. Let's say they have the angle theta in between them, theta in radians. Then we know that the cosine of theta is equal to u dot v over the absolute value of u time, well, not the absolute value, but the magnitude of the vector u times the magnitude of the vector v. And so, in other words, what I'm trying to get at is this: when we first learn about the inner product, we learned that the inner product can be used to capture geometric ideas, geometric can be used to translate geometric ideas into the world of vectors and vice versa. Okay, so but now so that was when we were thinking about vectors in 3 space like this, our familiar directed arrows, or as you probably have learned in your class, any vector of Rn. But for simplicity, R3, the ones that we can visualize. But of course, this discussion would work for Rn, right? We can find out the length, right? The length of a vector. Oh my God, that's too far apart. Is the square root of the inner product of the vector with itself, right? But this was in 3 space. So now the transition that's being made here is this: linear algebra talks about vector spaces. Vector spaces are spaces of objects that satisfy certain properties. These, which are the beginning example of the vector space, are very important. And of course, they're very familiar to us. They're easy for us to understand. We've got a lot of physical intuition, everyday intuition about these, right? We know if we walk 1 feet and we walk another, we've actually walked a total of 2 feet, and so on, right? But where we're going with linear algebra, oh, and also, let me make a brief point, and also these geometric ideas make sense to us. We've seen them in Calculus 3, and we see that the inner product captures those. They allow us to generalize these ideas, because this formula, for example, will work. Here I drew it in the case of a 2-dimensional space, so it makes perfect sense, and we can actually construct examples from geometry to show that they capture what we think they capture, right? But we can generalize. I can use this same formula to calculate the theta between two vectors in n space. Like, let's say n is 10. Now, in my brain, and in your brain, and in all human brains, to visualize that isn't possible, unfortunately. But we can use our mathematical ideas to generalize. Okay. And of course, I could ask you to calculate the dot product of this, and it would be easy. Okay, right? Because in that case, if I were to take, let's say, I was to take the dot product of u, or let me write this explicitly. So let's say I have I plus 3j, comma, and let's say 2I minus 4j, let's say. And let's say I'm using the normal dot product, not this dot product. We're not in this space. I'm doing this just to set the stage for us. Well, here, I know that it would be the coefficient of the I times the coefficient of the I here for this different vector. In this case, 1 times 2 is 2 plus 3 times negative 4, right? Which gives me 2 minus 12, which gives me a dot product of negative 10. Okay? So I can calculate the dot product of these two vectors. Okay? And let me see here. And this can give me information depending on what kind of information I want. For example, let's say I wanted to get the theta for this. What I would have to do is I would have to, for example, let's say this one was u, let's say this one was v. Here is the u dot v, in other words, the numerator of this fraction. And then for the denominator, I would calculate the magnitude of u by taking the dot product of this with itself and square rooting that. For the magnitude of v, I would take the inner product of this with itself, square root that. And then I would divide this number, negative 10, by the product of those two, which I could easily calculate using the same procedure. And then I could get the cosine of the theta. I could take the cosine inverse to get the theta, and I would get all those geometric information. Okay, anyway. But now, so that's the idea, like, before we actually, yeah. Okay, I'm going way too far on this, like, setup. I'm sure you already know this. So I know I'm not, like, I know I'm like probably boring you. Okay, now we're gonna get to the heart of the matter. I'm gonna use this first with the following. So first, I'm gonna start with an example to walk you through how this works. Okay, so this example captures how the dot product works. I mean, of course, I was totally summarized. I didn't give full information. I didn't give any proofs. I know that you guys covered that in your class, so I know it's okay. If you wanted me to give proofs of that or more discussion along those lines, I'd be happy to do so, of course. I don't want you to think that I wouldn't. But I want to move straight to this problem to give you as much benefit as possible with this problem. But before I do that, and also to help you the most with that, I want to do this example first. So this is saying that the inner product of two polynomials in the space of polynomials with degree at most 3 is given in this way. So in order to show you, like in order to set up how we're going to do these calculations, I'm going to do an example calculation first so you can see how to perform this dot product. And then afterwards, we're going to start going straight to the gram-schmidt process. Okay. So let's let, for our example, let's let p of x equal to 1 plus 3x minus x squared. Whatever, you know, whatever. And let's let q of x be, let's say, 2 minus 4x squared plus x cubed. Okay? I first ask myself, is this a member of this vector space? It is. Is this a member of this vector space? Yes. Why? Because they're both polynomials. They're both polynomials of degree 3 or less. And moreover, you can see that they are elements of the span of this basis. And therefore, they are in fact members of this vector space. The vector space, the p to the 3, which is, again, the vector space of all polynomials of degree no greater than 3, is the span of this basis. Okay. So now what I'm going to do is I'm going to calculate what the inner product of these two would be. So the inner product, okay, of PQ here. Oh yes, so there's a brief point I wanted to make. So I want to make a distinction of what's happening here from the previous example and why I brought that example in. So the previous example we did was just a discussion of what the inner product like came from, how we used it in the past, how it can be used to gain geometric information, ideas about how long vectors are, the angle between vectors, geometric ideas, okay, in a familiar space. And where, sorry about this. Sorry about that. That was just my cyanide capsule, you know, just cracking there. Nah, I'm just kidding. That's just a joke. No, I mean, okay. But so anyway, so the beauty of what we're about to do is that since the space of polynomials is a vector space, we can translate all the results for inner products that are proved for vector spaces to spaces that are not familiar to us. And of course, in this case, this is what we're doing basically is approaching uh, how do I want to call this? Well, let me let go of that for a moment. But what I want you to know is this: we're going to translate those geometric ideas to an abstract space where the ideas might seem slightly different, but they're going to be just as useful. Okay, let me just leave it there. But how do we calculate this inner product? Okay, so first of all, what is it? The inner product is going to be the integral from -1 to 1 of 2 times the p of x, which is that 1 plus 3x minus x squared, times the q of x. Okay, this is just normal multiplication. 2 minus 4x squared plus x cubed, and then dx. Okay, and then here, this is actually going to be a very straightforward integral. I'm just going to get it to the point where you can integrate it, and then I'm going to let you do that. Or maybe I'll do it here real quick if it's not too messy. Okay, let me do this product over here. Okay, so 1 plus 3x minus x squared, 2 minus 4x squared plus x cubed. Okay, so this is 2 minus 4x squared plus x cubed plus xx minus 12x cubed okay, 3x times x cubed, that's 3x to the 4th power plus, okay, and then here it'll be minus 2x squared, okay, where's my x, okay, nothing there, so I'll just put it here, minus 2x squared plus 4x to the 4th minus x to the 5th power. Okay, and then of course this will simplify to something. Okay, okay, the biggest one is x to the 5th, so minus whoops, x to the 5th power, x to the 4th, so I have 7, that's it, x cubed minus 11x cubed, yes, x squared, let me see, minus 2 minus 4 minus 6x cubed plus 6x, and then plus 2. So here I multiplied out those two polynomials, okay? And then of course, like, okay, so that'll be the integral from -1 to 1 of this, okay, times 2. So I'll pull the 2 out to the front, of course. It'll be negative x to the 5th plus 7x to the 4 minus 11x cubed minus x. What? What? Minus 6x squared, I'm sorry. And then minus plus 6x and then plus 2 dx. Oops. Okay. Now, here I could, because the boundaries of the integral are the same, I could zero out all the ones that are even and keep all the, zero out all the ones that are odd, keep all the ones that are even, do some integration tricks like that, but we're not going to do that, okay? Now, in actual fact, I know that you can perform this integral. Wait, should I do it anyway? Fuck. Yeah, fuck it, I'll do it anyway. Just like to make this example, I should have picked polynomials that would have come out easier, but you know, we can't pick them always. But in any case, I can tell from here that if I stopped right now, you would be able to finish off this integral and you would be able to get the scalar product. But let me just do it as, let me just finish off this example so it's completely professional, okay? So it'll be 2 times open parentheses. The integral of this is negative 1 over 6 x to the 6th power plus 7 over 5 x to the 5th power minus 11 quarters x to the 4th power minus 6 over 3, or 6 over 3 is 2, so minus 2x to the cube power plus x squared over 2, 3x squared plus 2x, evaluated from negative 1 to 1, okay? And then here, I'm going to evaluate it first at the positive one, and then I'm going to evaluate it at the bottom at the negative one. But to save time here, I do want to use a calculator here. And if this is like violating like any sort of like, oops, oh no, I hope it didn't make a sound. Oh no, okay. Sorry about that if that was loud. Negative 1 over 6 x to the 6th power, okay, plus 7 over 5 x to the 5th power minus 11 over 4 x to the 4th power minus 2 x to the cube power plus 3x squared plus 2x, okay, at 1. That gives me 89 over 60. And then I'm going to subtract negative 79 over 60. And so you can see that this will actually add to that, okay? So it'll be this minus and then times 2. Okay, 28 over 5. So look at this. I've taken 2 polynomials in the space of polynomials of order at most 3, of degree at most 3, and I have taken their inner product using our formula, and I have gotten their scalar product to be 28 over 5. Okay? Okay. And you could use this, and look, so this is what's magical here. Okay? So first of all, let me also make a comment here. Notice this is not 0. So these 2 vectors that I picked at random, I mean, the chances that they would be orthogonal is like nearly 0, right? But so we can see that right away. They're not 0. And and again, I picked them at random, so the chances that they could be 0 would be very low. Okay? What else do I want to comment here? Okay. Okay. Oh yes. So the other thing I wanted to mention was this. Remember our formula for the cosine of theta? This could be the numerator, and on the denominator, I could divide by the magnitude of the p, the magnitude of the q, the product of those magnitudes. I could divide this by the product. Oh my god. I can't believe it. My brain's just going in circles. I could divide this inner product value by the product of the magnitudes of the values of this one and this one using the same procedure I just did. Like, for example, the magnitude of p, how would I get it? This would have been p, and this would have been p also. I would have done the same procedure. I would have gotten a different value, of course, which would be the square of the magnitude. I would have square rooted that. Same thing for the q. multiply those magnitudes, and then divide this value by that product of the magnitudes, and that would be giving the cosine of theta that lies between these two functions when these functions are looked at as vectors in this vector space. Okay, that's mind-blowing. Anyway, but I just wanted to make that point before we continued on because it's a beautiful thing, okay? Okay. What is a beautiful thing? Abstraction, okay? That because these properties, these geometric properties, are proven for vector spaces, we can translate those properties to any space that has those vector space properties. Okay? Okay, I'm gonna shut up now. So now now that we've seen this example of how we can actually use the inner product formula that they give us to calculate the inner product in this vector space, we're gonna actually go ahead and calculate the orthogonal bases. Okay? Okay. I take as an example, okay? Let's say x squared plus 1, and let's say q of x is equal to x cubed, let's say. I picked these so that they would be simple. Now the inner product of p times q here will be, oh shoot, I'm not even writing my notation properly, will be integral from -1 to 1 of 2 times, okay, p of x, what is my p of x? X squared plus 1 times my q of x, which is x cubed, okay, dx. Now what is that? I can pull this 2 out, of course, right? Integral, -1 to 1. Now I can multiply this out. I shouldn't have written that there. That's just a multiplication, but it confuses us with, because there's x's here. So that would be x to the 5th, and then plus x third. Oh no! Okay, so obviously you know that this will become the integral from x I didn't want to do this, but I noticed right now as I was just doing this that if you were to take this integral, you get x to the 6 over 6, and when you evaluate that at these endpoints, it actually zeroes this term out, and similarly this term gets zeroed out. So it actually turns out that these two polynomials are orthogonal in this vector space. Okay, that means to translate our geometric knowledge, these are sort of perpendicular in this vector space. It's crazy. Okay. 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 But so now I hope you see how you can use this inner product in this vector space. And that's going to be critical right now because we're about to use it in the gram-schmidt orthonormalization procedure. Okay. Now it's orthonormalization because we're going to not only calculate vectors that are orthogonal, we're going to calculate vectors that are orthonormal. That means that okay, what does that mean? That means the following. Okay, for reasons that will later become more clear, I'm going to use the following notation. I'm going to let this be my y1, this will be my y2, this will be my y3, this will be my y4, okay? And my orthonormal basis, I'm going to denote as x1, x2, x3, and x4, okay? Okay, so what properties do I need for my basis to be orthonormal? I need the following facts. If I have xi dotted with xj from my orthonormal vectors, then it'll equal to 0 if I does not equal j, and it equals 1 if I equals j. So first of all, this is the orthogonality condition, but it's also capturing the orthonormal condition because if the dot product of, let's say, x1 with x1 is 1, then that 1 corresponds to the square of the magnitude. And so when I square root it, I'm still going to get 1, and that tells me that the magnitude of the x1 itself, for example, in the case that I've just mentioned, would be 1. And also, it's telling us that if the I is not equal to j, that they're orthogonal, because the x, like let's say I was 1, j was 2, then x1 times x2, or times in the inner product sense, equaling 0 means they're orthogonal. So number one, they're orthogonal, pairwise, and they're have magnitude, and they each have magnitude 1. And what I want you to notice from this is this captures exactly, going back to like the familiar example of Rn, just like in calculus 3, right, which is the n space, like let's call the coordinates x1, x2, dot dot dot, all the way to xn, right? Let's say the span of these, right? But we know that, like, if we pick our standard basis vectors where ej is equal to 0, 0, 1, where this is 1 in the jth position, right? This captures exactly the property we'd expect for the standard basis vectors. Like if I have E1, which is 1, let me say in R3, so it's more familiar. But you can tell this argument will work perfectly. You know that if E1 and E2, like let's say, and E3, like this, you can see that if I take the dot product of this one with itself, it'll get 1. This one with itself will be 1 also. This one with itself will be 1 also. But if I take the dot product of this, I get 0. The dot product of this one and this one, I get 0. The dot product of this one and this one, I get 0. And etc. All of the possibilities, right? And so in other words, this characterization of orthonormality captures the idea of our familiar example of the standard basis vectors in R3, that beautiful, easy to use basis that we like, okay? And it shows us what we're aiming for, okay? Okay. Okay. So, okay. So this is the inner product. This is the space, the inner product space that we're going to be dealing with. We have our basis, which is going to be the basis they gave us, actually. 1, x squared, and x cubed. The vector space is the set of all polynomials of order at most 3. We're going to label the orthonormal basis vectors we get as x1, x2, x3, and x4. We're going to label the vectors of the basis they gave us as y1, y2, y3, and y4, as I've labeled here. This is the gram-schmidt orthogonalization procedure, okay? And I'm using the notation from this book by Peter Lax. It's I highly recommend it. But your textbook will have the same formulas. They just might be dressed up differently, okay? But in any case, what we're going to do is we're going to begin now, okay? Okay. So the first thing we're going to do is we want to try to get the first, well, not try, we're going to try to get the first vector from our orthonormal set. What we're going to do is we're going to have to take this vector, which we're labeling as 1, but we're going to have to normalize it. We're going to have to make sure that the vector x1 has magnitude 1, okay? And we don't know if 1 has magnitude 1. So what we're going to do is we're going to test it, okay? We're going to find out, so what is the magnitude of y1? The vector from the original vector basis. Well, the magnitude of y1 will, of course, be, well, the square of it at least, will be the inner product of y1 with itself, okay? Because that's what we were saying here, right? If I square it, I'll get the inner product. And the reason why I'm writing it like this is because this will be easier for us to calculate. Now here, so here, of course, what is y1? y1 is just 1, so it's the inner product of 1 with itself in this vector space with this inner product. Now what is that? This inner product, we can calculate it as follows. It'll be the integral from -1 to 1 of 2 times p of x, which is 1, times q of x, which is 1 p q dx. That's just 2. 2 times the integral from -1 to 1 of dx. Now what is that? That's going to be x. So it's going to be 2 times x from -1 to 1. This is going to be 2 times 1 minus -1. Okay? And of course, you know that 1 minus -1 is 1 plus 1, or 2. 2 times 2 is 4. Like this. Okay? So that tells us that the square of the norm of 1 is 4. That means that the norm of 1 is the square root of that, which is 2. So what we've just determined is that in this vector space with this inner product, y1 has a magnitude of 2. So what I'm going to do to make my first basis vector for my orthonormal set is I'm going to normalize it. How am I going to do that? I'm going to divide the vector by this quantity. Okay, so our vector is 1. I'm going to divide it by 2, so I'm going to get 1/2. Okay, so that is my first member of my orthonormal basis. Okay, so now let us proceed to calculate the next term of my orthonormal basis. Okay. Okay. Let me see here. Oh, yes. Okay. Okay. So now we're going to have to translate this formula into a practical case. I'm going to start off, as you can imagine, by calculating x2. Okay. So my x2 is going to be the constant times the y2, okay, minus the sum from 1 to 1. 1, 2. In this case, our k is 2. 2 minus 1 is 1, and that's why it's 1 on top of the cj times the xj. Okay? Now notice that the cj is the yk times the xj. So let's do that here. This is going to be c times the y2 minus, here it's just going to be one term, c1, x1. What is my c1? My c1 is going to be the yk, in this case the y2, inner product with the x1. So my y2 inner product with my x1, which is 1/2, we calculated that already, times my x1, which is 1/2. Like this. Okay? Perfect. So now I'm in the position to plug in for the y2, and I'm also in the position to, I mean, strictly speaking, what I should have done is I should have put an x1 here and x1 here, so it would have been still in general, but I kind of jumped the gun there. Now the y2 here is going to be the x. Okay, so I'm going to plug those in the next line, and then we're actually going to calculate the bits of it that we need to get. So the y2 is x minus inner product of x with 1/2 times 1/2. Okay? So now, okay, the first thing we need to calculate now is the x 1/2, like this. The inner product of x with 1/2 in this vector space with this inner product. Okay? The integral from -1 to 1 of 2 times p of x. What is my p of x? It's x. What is my q of x? It's 1/2 dx. This is very nice, right? So you can see here that 2 times 1/2, it's 1. So we're left with just the integral from -1 to 1 of x dx. That's going to be 1/2 x squared from -1 to 1. Now you can already see from here, what is this going to be? This is going to be 0. Because when I evaluate this at 1, x squared is going to be 1. When I evaluate this 1/2 x squared when I evaluate the x squared, the x squared at -1, it's also going to be positive 1. So I'm going to end up having 1/2 times 1 minus 1/2 times 1, which is going to be 1/2 minus 1/2, which is going to be 0. Right? So here it turns out that that term goes to 0. This goes away. Okay? It goes away completely. And we're left with just c times x. Okay? Okay, so in other words, this is c times x. Okay. What we have found is that our second member of our orthonormal basis is going to be a constant times x, but we need to find out what constant will make it happen. So how are we going to do that? What we're going to do is we're going to normalize this vector. So we're going to we're going to force the norm of this vector to equal 1 so that it will be normalized. Okay, let's do this. So I know, in other words, what I'm saying is I want to set 1 equal to the norm of x2 squared, which will equal to the x2 with itself. What does that mean? Well, we know what x2 is now. It's c times x. We don't know what c is, but we're going to find it. Okay? So it's going to be cx times cx. Like this. Okay? Now we're in a position where we can actually use our formula. We know how to find the inner product of cx with itself in this vector space. It's going to be the integral from -1 to 1 of 2 times the p. What is the p of x? Cx. What is the q of x? Cx. Okay? Now you can see that I can have 2 times c, that's 2c squared. I'm going to pull that out, and I'm going to be left with the integral. So 2c squared times the integral from -1 to 1 of x squared, okay, dx. Now when I integrate that, I'm going to get x cubed over 3. So I'm going to get 2c squared over 3 x cubed evaluated from -1 to 1. Okay, and then this becomes 2c squared over 3, and then it's going to be 1 cubed minus -1 cubed, like this, right? -1 cubed is actually -1. So I'm going to be left with 1 minus -1, which will be 1 plus 1, which will be 2. So this will end up being 2 times this fraction, which becomes 4c squared over 3. Like this. So look what I've done here. I have calculated what the square of the norm of x2 is, given that we don't know what c is yet. But I know that whatever c is, it will be 4 times c squared over 3. And if I force it to equal 1, then that means I have to force 1 to equal that. So I need to force 1 to equal 4c squared over 3. Now you can see if I multiply both sides by 3/4 and I square root it, then to make this condition hold, I'm going to have c equals to the square root of 3 over 2. Okay? And there you have it. Okay? The second component of our orthonormal basis, given by the gram-schmidt procedure here, is the square root of 3 over 2x. Okay. So now what we're going to do is we're going to calculate our third member of our orthonormal basis. Okay? Yes. Oh my god. Oh my god. Okay. Okay. Now we're going to calculate my x3. Now, that is going to equal to c times y3 minus the sum from 1 to 2. Okay, because 3 minus 1 is 2 of my cj xj's. Okay, so I'm going to expand this out right here in a row. It's going to be c, again a constant that will be determined at the end, times my y3 minus, it's going to be the sum, so I'm going to have like here c1 x1 plus c2 x2, and in this case that's it, because of course the sum goes from 1 to 2. Okay, now this is going to be c times my y3 minus, okay, my c1 x1. My c1 in this case is going to be the inner product of my y3 in this case x1 times x1 minus the inner product of y3 x2 with x2, like that. Perfect. Okay, and now I can actually plug in from the stuff that we have over here. So it's going to be some constant times my y3. My y3 is x squared minus the inner product of x squared, oops, with my x1, which is 1/2, and that times my x1, which is 1/2, minus my y3, which is x squared, times my x2, which is square root of 3 over 2x, times the square root of 3 over 2x. Okay. Okay. So now what we have to do is we have to calculate those inner products, and then we're going to have to simplify this whole thing. Okay. Now, if you, yeah, so let's do that together here. Okay. So I'm going to leave a space here for this row, which is going to happen right now. So c x squared, and then, okay. First of all, what is the inner product of x squared with 1/2 in this vector space? It's going to be the integral from -1 to 1, okay, of 2 times p of x, which is x squared, times q of x, which is in our case 1/2, okay, and then times dx. Now here, 2 times 1/2 is 1, so this simplifies to the integral from -1 to 1 of x squared dx. And then I can integrate that. I get 1/3 x to the cube, right? So it's 1/3 and then x cubed from -1 to 1. You can tell that, and then here I can plug in. So it'll be 1 cubed minus -1 cubed. Of course, the -1 cubed will be -1. The 1 cubed will be 1, so I'm going to be left with 1 minus -1, or in other words, 1 plus 1. So it'll be 2. 2 times 1/3 is 2/3. Okay. So this coefficient, okay, is 2/3. So it'll be x squared minus 2/3 times 1/2. Okay. Now I need to calculate this coefficient here. Okay. Let's do that together. Okay. So what is the inner product of x squared times what is the inner product of x squared and 3/2 x in this vector space? Okay, so now I'm going to use this formula again. It's going to be the integral from -1 to 1 of 2 times px, which is x squared, times qx, which is square root of 3 over 2x, dx. Now, the square root of 3 over 2 times 2 will leave us with just a square root of 3. So it'll be the square root of 3 times the integral from -1 to 1 of x cubed dx. Now, you can probably already tell that this is going to be, well, I'll just go forward with it. But basically what I was going to argue is that you can see from this integral that it's actually going to go to 0. Okay. So, yeah, this part is going to go to 0. Okay. But, so let me show you why. If I integrate the x cubed, it's going to be x to the 4th over 4. And of course, if you plug in the 1 at the top, it's going to be positive 1 when you take the 4th power of 1. When you plug in the -1 at the bottom, it's also going to be positive 1 because -1 raised to an even power is positive 1. And so you're going to have 1 minus 1, and that's going to be 0. 0 times that, that's just going to be 0. Okay? And so that contribution of the square root of 3 over 2x in this expression goes to 0. So we're left with just this here. Okay? Okay. And so now what's going to end up happening is that we're going to, we basically are going to have, right now, we basically have our x3 up to the normalization constant. So let me just delete all this and put this there. Or wait, do I have enough room? No, yeah, I'll do it down here. Wait, yeah, let me do it down here. It's fine. So let me just write this down over here. So this will be c times x squared minus 2 over 6, or that's 1/3. Yeah, that's right. Much better. So, okay, what do I mean by normalization constant? I want to find out what c will make this vector to have a unit length. That is to say, again, just as before, I want to force 1 to equal the norm squared of x cubed. Really, I want to have the norm to be equal to 1. But if I square it, it'll still be 1. So this condition will still make what I want to have happened. But what is this? This is the inner product of the x3 with itself. Right? Do we know what x3 is? Up to a constant. Right? We want to find out what this c is. But I can use that here. In other words, what I'm saying is, I'm going to take the inner product of c x squared minus 1/3 with c x squared minus 1/3, like that. Okay? Now, how do I do that? Well, I have my inner product formula of this inner product space. So it's going to be the integral from -1 to 1 of 2 times my p. What is my p of x? It is c times x squared minus 1/3. What is my q? Oh, oops. What is my q? It is c times x squared minus 1/3. Right? Dx. Right? Because this is my p of x, this is my q of x, and so therefore my inner product of the p times the q will be 2 times the p of x times the q of x, integrated from -1 to 1, 2 times the p of x times the q of x, integrated from -1 to 1. You can see that I'm going to have a 2 times c, which will be a 2c squared again. I'm going to pull that out of the integral. What's happening on the inside? I'm going to have an x to the 4th power. I'm going to have a minus 1/3 x squared, minus 1/3 x squared. In other words, minus 2/3 x squared. And then I'm going to have a negative 1/3 times the negative 1/3, which will be a plus 1 over 9 dx, like this. Okay? And then here, you carry out this integral. Okay, I'm going to need more room here. Okay, do I want to? Yeah, okay. No, it's okay. I can continue going here. Okay, so this is gonna be 2c squared open parentheses 1/5 x to the fifth minus that's gonna be x to the third. So 2 over 9x cubed plus 1 over 9x, all evaluated from -1 to 1. Okay. I'm sorry about the way this is turning out over here, all filling up the board like this. Okay. So now what I'm gonna do is I'm gonna calculate what the inside is at the both ends of the calculation, and then I'm gonna incorporate this 2c squared, and we're gonna like work on that. I'm just using the calculator here to help guide us with what these numbers must be. I could do it by hand, but it would take us forever, and I know that that's not, that's not good. Yeah. So I'm gonna first plug in 1. Okay. So I get 2c squared open parentheses 4 over 45 minus, okay, negative 4 over 45. So when you have 4 over 45 minus negative 4 over 45, that becomes 4 over 45 plus 4 over 45, which becomes 8 over 45. 8 times 2 is 16 over 45. So this simplifies to 16 over 45 c squared. Right, and remember, what we're trying to do is we're trying to force the 16 over 45 c squared to equal 1. Well, if you multiply both sides, so let's write that down over here. What we're trying to do is we're trying to force 16 over 45 c squared to equal 1. Because that will allow the norm of this vector to be 1. So I'm going to multiply both sides by 45 over 16. And then I'm going to square root it. So I'm going to have c is equal to, the square root of this will be square root of 45 over 4. But then 45 is 9 times 5. So it'll be 3 square root of 5 over 4. And so that's the c that's going to be in our expression here. Okay. So now I can put that over here. So it's going to be 3 square root of 5 over 4 times x squared minus 1/3. Yes. Let me get rid of all this rigmarole. Okay. Yeah. Okay. And now we're finally about to get the final basis vector using the gram-schmidt orthogonalization procedure. Okay. I apologize that this calculation is taking us this long. I hope that you're understanding it. Yes, very nice, very exciting. Yes, very good. Yes, very nice. Okay, good. Now, finally, the x4. So now, again, we're going to use this formula, and we're going to expand it out here at the top first. Then we're going to expand it a little more. Then we're going to expand it a little more. And then in this case, for this one, I'm going to leave the final expression on the top, and then I'm going to start doing the calculations because there's going to be more of them, as you can already imagine. So for the x4, it's going to be a constant, the normalization constant that we're going to do at the end, times my y4, right? I'm going to incorporate our final basis vector minus the sum, right? From 1, 4 minus 1 is 3. From 1 to 3, right? Because remember, we only have to remove the projection from these 3 vectors of the CJ xj's, like this. So now we're going to expand this, and I'm just going to distribute the negative in this next line to save space. So it'll be the constant times the y4 minus the inner product. So the C1 x1 will be, if I use this, it'll be the y4 comma x1 times the x1 minus the y4 x2 with the x2 minus the y4 with the x3 times the x3, like that. Okay? Yes. And so you see what I'm doing is I'm removing the projection on each of the previous basis vectors we've gotten to make this new vector orthogonal to the previous 3. But because it has the y4, any linear combination of the y1, y2, y3, and y4 will be in the span of the x1, x2, x3, and x4, except that the x1, x2, x3, x4 will be an orthogonal set, and moreover, it's going to be an orthonormal set, which is exactly what we're looking for. Oh my god, my poor brain. Okay, oh my god, I needed that. Okay, so now we're going to plug in with these things. So the constant times, my y4 is x cubed, okay, minus the inner product of x cubed with my x1, which is 1/2, times my 1/2, minus the inner product of x cubed with my x2, which is square root of 3 over 2x, times the square root of 3 over 2x, right? Minus my y4, which is my x cubed, times my x3 in inner product terms. Let me just go over here. Oops, sorry about that. 3 square root of 5 over 4 x squared minus 1/3. And then that inner product times the 3 square root of 5 over 4 x squared minus 1/3. Okay? I apologize that it's kind of like tilted off, but you can see what that is, right? Let me verify that you can see it. Okay. Basically, it's just, wait, should I? No, yeah, let me not do that to you. Let me write it in very nicely. I have to. Yes, I have to. I want to make sure you can see it. Minus the inner product of the x3 with the 3 square root of 5 over 4 x squared minus 1/3, and then that inner product times the 3 square root of 5 over 4 times the x squared minus 1/3, like that. Okay, all of that times this c. So what we're going to have to calculate now is these coefficients to find out how much each of these contributes, or how much of these contributions, these projections, we have to remove from the x cubed. Okay? Okay. So let us start with this calculation here. What is the inner product of x cubed with 1/2 in this vector space? It's going to be the integral from -1 to 1 of 2 times the p of x, which is x cubed, times the q of x, which is 1/2 dx. Okay? 2 times 1/2 is 1. So I'm left with just x cubed. So it's going to be the integral of x cubed dx from -1 to 1. Now here, that'll become 1 over 4 times x to the fourth power evaluated from negative 1 to 1, which will be 1/4 times 1 to the fourth power minus negative 1 to the fourth power. Now, you can see here that negative 1 to the fourth power is positive 1. 1 to the fourth power is positive 1. 1 minus 1, 0. So the contribution of this term is gone. Okay, this goes to 0. Okay. Now we need to figure out what the contribution of this term is. Let's do that together here. Okay, what is the inner product of x cubed with the square root of 3 over 2x? Okay, that's what we need to know. Let's do it together. This is equal to the integral from negative 1 to 1 of 2, right, times my p of x, which is x cubed, times my q of x, which is this expression here, square root of 3 over 2 x dx. Now, you can see that 2 times the square root of 3 over 2 becomes just square root of 3. So this is the square root of 3 times the integral from negative 1 to 1 of x cubed times x, that's x to the fourth power, dx. Okay? Okay. Now, this will actually give us the square root of 3 over 5, because the integral of x to the fourth is x to the fifth over 5. And then it'll be x to the fifth evaluated from negative 1 to 1. That's going to be the square root of 3 over 5 times 1 to the fifth power minus negative 1 to the fifth power. Now, negative 1 to the fifth power is negative 1. So, and 1 to the fifth power is 1. So it'll be 1 minus negative 1. That'll be 1 plus 1, which will be 2. And so it'll be 2 square root of 3 over 5. Okay. So we know that this will be 2 square root of 3 over 5. So let me actually write that down in here so we can start keeping track of what it is. Okay. Let me put a little dotted line here so we don't lose the track of where we are. So this will equal to c, this constant that we have to calculate, times x cubed. This is gone, minus 2 square root of 3 over 5 times what? Times the square root of 3 over 2x. And then finally, what we have to calculate is this contribution here. Okay? Okay. Okay, let's do that together now. Okay. So what I have to do now is I have to calculate this inner product. Okay, let's do that together here. What is the inner product of x cubed 3 square root of 5 over 4 x squared minus 1/3? Like this. What is the inner product of these two polynomials in this inner product space? Let's write the integral over here. It'll be the integral from negative 1, to 1 of 2 times the p of x, which is x cubed, times the q of x, which will be this monstrosity, 3 square root of 5 over 4 x squared minus 1/3, okay, dx. Now, I can pull out those constants, and I can get that this is equal to, let me see here, 3 square root of 5 over 4, 3 square root of 5 over 2 rather, because that 2 times the 1/4 becomes 1/2, integral of, from negative 1 to 1, of x cubed times x2, that's x to the fifth power, minus 1/3 x to the cubed power, dx. Now, I have good news for you here. Look at what's going to happen to this integral. When I integrate x to the fifth power, I'm going to get 1 over 6x to the sixth power. When I evaluate that at these two limits, it's going to disappear. What about the x cubed term? When I integrate the x cubed, I'm going to get 1/4 x to the 4th power. And when I evaluate that from -1 to 1, that's also going to disappear. So this whole contribution goes to 0. So this whole thing over here also goes to 0. Okay, so I'm left with just this. Okay? Yes. And so now, I hope that you got that. I'm pretty sure you did. So like, I'm not gonna belabor it, but if you want me to do that explicitly later, I'll do it for you. Okay. So now we're here. Let's just clean it up a little bit first. So this 2 cancels with that 2. Square root of 3 times square root of 3, that becomes 3. So basically this is going to be c times x cubed minus 3 over 5x. So now we know what what the 4th orthonormal basis element is up to a constant. We know it's a multiple of x cubed minus 3/5 x. In order to give us enough room to calculate the normalization constant, I'm going to erase this work. And I'm going to replace our current expression up here. Okay? So our current expression for the x4 is the constant, which we're about to calculate, x cubed minus 3/5 x. Okay? Like this. Okay. 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 So now, what we need to do to normalize this one is we need to force the norm of x to the 4th. We need to force it equal 1. So what's that going to be? It's going to be like this. But what is x to the 4th? It's this expression here. So I want to find the inner product of c times x cubed minus 3/5 x, oops, with itself, which is c times x cubed minus 3/5 x. Like this. How do I do that? Well, again, our trusty friend, -1 to 1 of 2 times our p of x, which is c, x cubed minus 3/5 x, times our q of x, which is c times x cubed minus 3/5 x dx. Okay. I can pull out a 2c squared just as before. Integrate -1 to 1, x to the 6th power, right? Minus, let me see, that's going to be x to the 4th, right? So -3/5 x to the 4th minus 3/5 x to the 4th is going to be -6/5 x to the 4th. And then it's going to be plus 9 over 25 x squared dx. Okay? Let me make sure. Yes. Now I'm going to integrate this. That's going to be 2c squared open bracket 1 over 7x to the 7 minus 6 over 25x to the 5th power plus 9 over 75x to the cube power from -1 to 1. Okay. Then here, so this then gives us 2c squared open bracket 4 over 175 minus negative 4 1 over 175, which will then become plus, because the minus will become plus, so it'll be 8 16 over 175. So in other words, we have gotten to the situation, okay, let me write that down here. 4 plus 4 is 8, times 2 is 16, c squared over 175. Okay. So now that I have to force it equal 1, right? I want 16c squared over 175 to equal 1. You can tell I'm going to multiply both sides by the reciprocal of 16 over 175. So I'm going to have c squared equal to 175 over 16. I'm going to square root that, and I'm going to get c equals to the square root of 175 over 4. Now, 75 is 3. No, wait. 175 is 7 times 25, so it'll be 5 square root of 7 over 4. Okay. So then here, so that's the c that will make it equal to 1. By the way, I'll show you how to do that right now. Okay, so this is 5 square root of 7 over 4 times x cubed minus 3 over 5th x, like this. Okay. Let me show you how I did that square root over here. Okay, what is the square root of 175? So the square root of 175 is equal to, we know that 175 is 3 times 25, so it'll be the square root of 3 times 5 times, I'm sorry, not 3, 7 times 5 times 5, right? Let me see. Yes. And so you can see here, this pair of 5s, I can pull it out of the square root, so it's 5 square root of 7. So that's how I got the numerator. And the bottom is just the square root of 16. 4 times 4 is 16. So finally, we have our orthonormal bases. 5 square root of 7 over 4 times, now I can get rid of all of this rigmarole. X cubed minus 3/5 x. Where's my brain? Okay, let me see here. Okay, that's it. Let me pause this.